Everybody hear me all right?
Yep.
My name is Murray Camp, and I live in Dallas, Texas. I appreciate you guys having me out. Today, we're going to talk about probiotics and labile organic carbon dosing. There's a lot of material in this presentation. If some of this stuff kind of seems a little over your head, don't worry, it seemed over my head when I first started trying to wrap my brain around it too. So I'll be here, until tomorrow. And if you have any questions whatsoever, please grab me and I'll do my best to explain it to you. So when we talk about probiotic systems, what are they and what are they supposed to do? I think a good way to start is to look at the definition of probiotics. And one definition by the WHO defines probiotics as live microorganisms which, when introduced into a system, confer some kind of health benefit on the host. So applied to our tanks, what we're really talking about is actively and proactively manipulating the species and strains of microbes, specifically bacteria, in our systems in order to achieve certain results. In reef aquaria, we're not only talking about managing the strains, but the densities of those strains, the amount of a given species or strain of microorganism. We're also talking about conceptually increasing the total biomass of the bacteria in order to reduce dissolved nutrients in our systems, and also to use bacteria as a potential supplemental feeding methodology for the corals that do feed on bacteria. Now, we see this term used in the hobby literature quite a lot, ULNS, or ultra low nutrient system. That's a reef geek's term of art. It's not a scientific term. When hobbyists use it, what we're really trying to say is a abiotic state in our tanks that more closely resembles the levels of dissolved nutrients you would find in waters adjacent to coral reefs. Or another way of saying it is a shift from a eutrophic, high dissolved nutrient environment to an oligotrophic or low dissolved nutrient environment. But really, in terms of the hobby, what we're talking about are nitrate values at 2 parts per million or below, and phosphate values at 0.03 parts per million or below, measured with commonly available hobbyist grade test kits. So when we see this term, that's kind of what we're talking about. We're talking about a low nutrient for an aquarium situation. Why do we care? What's the benefit of having a low nutrient tank? Well, in certain corals, you'll have increased colors from reduced zooxanthellae densities. In other words, the actual density of the symbiotic algae living in the outer layers of the coral tissue will be less, so you can see the colors, the pigments of the coral actually shining through underneath. You get a more colorful coral. You're not really affecting the pigments themselves through manipulating bacterial strains and species, but you're manipulating the density of the zooxanthellae. You'll also see enhanced skimmate production. This is a big one, elimination of nuisance algae, and in certain circumstances, perhaps an increase in the calcification rate or growth of hermatypic corals. So we're talking about bacteria. That's the core concept here, is manipulating bacteria. Well, what do they do in our reef tanks? Well, we know they consume nutrients, and they constitute a significant food source for certain genera of corals, especially those in the acroporid, pocilloporid, Porites, Montipora, those types of genera. Now, there's different types of bacteria. Essentially, we're concerned with the differentiation between heterotrophic and autotrophic bacteria. Heterotrophic bacteria use dissolved organic compounds for their carbon source. In other words, every living thing, in addition to a wide range of nutrients, needs a source of carbon. And heterotrophic bacteria gets that carbon from dissolved organic compounds in the water. They eat, in other words. The cool thing about heterotrophic bacteria is they grow quickly. If you can manipulate the amount of carbon and the right types of carbon available to the bacteria, you can directly influence the density of that type of bacteria. Autotrophic bacteria, on the other hand, fix carbon dioxide for their carbon source, and they grow much more slowly. They're really hard or harder to manipulate. They're both involved in processing nutrients, but we can manipulate heterotrophic bacteria more easily. And many studies suggest that heterotrophic bacteria in reef waters are responsible and critical players in nutrient cycling loops, including the processing of phosphate and nitrate in reef waters. Sorry, I know this is a little fast. I'm trying to blow through some of the science just to get a background on it. And then we'll talk about products and start looking at eye candy. But I don't want to get too bogged down into science because it gets a little dry. Well, so if heterotrophic bacteria need to eat, they need to pull nutrients out of the water column. What do they do with the nutrients? Well, they build cellular membranes with them. They build a wide variety of cellular structures. Some bacterial species will actually sequester or store nutrients in cellular membranes and other structures. They use these dissolved nutrients to reproduce, to create these really cool structures called biofilms that we'll talk about in a minute. Use them to build DNA and use them in multiple metabolic functions. So we've got all these nutrients, these nitrates, phosphates in our aquaria. And if we get the bacteria to increase their uptake of these nutrients, the bacteria can use them in everyday metabolic and growth structures and processes and take them out of the water column. In terms of bacterial involvement in nutrient cycles, it's an incredibly complex cycle and system, and we don't have a full understanding of exactly what's going on. And we know it involves multiple strains and species. We know that one species can be involved in processing different types of nutrients in a nutrient cycle. We know that in certain circumstances, one species will actually hand off the cycling of a particular nutrient to another species for further metabolic processes. But we can't say with absolute certainty in a reef environment, these types of strains do process nitrate into nitrogen gas. These specific strains sequester phosphate and process those nutrients out of the system. We've identified some, but not all. Here are some that we've obviously identified in the nitrification loop, some others in the denitrification loop, but we still have a very incomplete understanding of what specific strains are involved in all the circumstances. But keep this in mind. 1 liter of seawater can contain over 20,000 different species of bacteria. So trying to get our brains around how bacteria are involved in reef waters or any marine environment, how they're involved in processing nutrients is a huge task. But fortunately, we don't have to do that. One thing before we start moving into the next phase, I want to touch briefly on phosphates. It's been my experience as keeping reef tanks for almost 20 years that nitrate's a pretty easy nutrient to get your hands around and control, but phosphates become much more problematic. But what we've known is that many strains involved in the nitrogen cycle are also involved in the mineralization of phosphorus. So you can have one species or strain of bacteria that's involved in many different types of nutrient cycling activities in your system. One thing that some bacteria use phosphates for are building cell membranes, DNA, RNA, again, and biofilms. And here's what I want to get to about biofilms. All a biofilm is a community of bacteria. They're an aggregate of bacteria where the cells are actually stuck to each other and also to this sticky stuff, this EPS. It's this it's a natural polymer that's secreted by the bacteria for the bacteria to live in. So it's a community of bacteria. This stuff, this EPS, the architecture of these communities, guess what they're made of? Well, they're made of DNA, of proteins, of polysaccharides, a wide range of organic molecules, which are in turn are made of things like nitrate and phosphate. My point is, in order to build these biofilms, bacteria need sources of nitrogen and phosphorus to sustain their communities. And we've got plenty of that in our tanks. Another way of looking at it is, bacteria need carbon in addition to these other nutrients in order to build biofilms. So biofilms are a good thing. Here's a picture of one. This is actually a terrestrial biofilm, but this is the EPS, this extrapolaric substance that's secreted by the bacteria. We've all heard that, our standard conventional wisdom is that nitrification, the conversion of ammonia and ammonium into nitrite and then nitrate, is a aerobic process. In other words, bacteria need access to oxygen in the water column in order to carry on that nutrient cycle. And to a large extent, that's true. But bacteria embedded on the outside layers of these biofilms have free access to this oxygen and can engage in nitrification. While in the same biofilm, but even just a little deeper, the water gets more anoxic and denitrification occurs. What I'm trying to set up here is that nitrification, denitrification, phosphate metabolism, all of these processes are occurring in the same micrometers thick biofilm. You'll have different strains and species of different bacteria adjacent to each other in these biofilms, so it's tightly cycled. These chemicals and other materials don't have very far to go before they encounter another microbe that's going to process them on down the chain. And this really didn't have that much to do with what we're talking about, but I think it's so cool I want to share it with you. They documented quorum sensing in biofilms, which is that these bacteria, not only of the same species, but of different species, talk to each other chemically and know when they have critical densities of a given type of bacteria to begin building a biofilm. So the picture I'm trying to paint is that these aren't just germs and slimy stuff. These are complex, sophisticated communities of microbial life that are responsible both in our tanks and in reef waters for a tremendous amount of nutrient cycling. The bacterial biomass on and near coral reefs is enormous. One study showed that just by bacterial plankton, that is bacteria that are free floating in the water column, can reach densities of 2 million per milliliter of seawater. And benthic, growing on biofilms, on sediments, on coral rock, on corals themselves, can be high as 100 million bacteria per cubic centimeter. So I like to look at a coral reef as really a bacterial community with some other things like fishes and corals growing within it. And I think that analogy applies to our tanks as well. Densities of bacteria are higher in areas where there's higher nutrients, like mangrove communities, areas with higher runoff. But they're still, in any ecological niche, extremely dense. There hasn't been any specific long-term peer-reviewed study on bacterial densities in reef aquaria of which I'm aware. But the success of some of these systems we're about to talk about, and I promise you we're about to talk about it, we're about to get some useful information, suggests that in our tanks we have much lower densities of bacteria than you will find in waters adjacent to coral reefs or in most marine environments. And certainly the success of some of these systems seem to indicate that the bacterial densities in our tanks don't even approach what they would in the wild. So, take a breath. That was all really interesting, Murray. Why do I care? Well, I'm suggesting that increasing the bacterial populations in our tank so that we have lower dissolved nutrients is a good thing. Well, that's great, but how do we do that? Well, to reproduce, bacteria need, in addition to other parameters, but in terms of nutrients, they need a source of nitrogen, source of phosphate, source of carbon. I don't know about your tanks, but I don't have any problem with nitrate and phosphate. I got plenty in my tanks. Even in using good hobbyist grade test equipment, if you're reading 0.001 on a photometer for phosphate, you still have significant amounts of phosphate in your system. The same with nitrate. We'll talk about nitrate limitation in a minute, but generally you got plenty of nitrogen and phosphorus. But the problem is carbon. There's a thing in oceanography and in biology called the stoichiometric ratio. And all of this is trying, if you took a given unit of mass of any living thing and broke it down into its constituents, what would the ratio of carbon to nitrogen to phosphorus be? And with phytoplankton, for instance, it's 106 to 16 to 1. With bacteria, it varies, but you're going to get somewhere in this neighborhood. The point of this being, all you need to grow bacteria is a little bit of phosphate, a little bit more nitrate, and a lot of carbon. So what we're really saying is that our systems are carbon limited, at least in terms of the types of organic carbon that can be readily utilized by the heterotrophic bacteria that we're trying to get to grow. So, how do we address a carbon limitation? How do we increase the carbon? Well, there's many sources of organic carbon that aquarists use and that heterotrophic bacteria can utilize pretty readily. Ethanol is a common one. We're going to talk about vodka dosing here in a minute. Acetic acid, vinegar, various sugars, including glucose and sucrose, ascorbic acid, vitamin C, acetate, and there's plenty of sources of organic carbon that marine microbes will use to live and grow. And I put acetone and naphthene in red here because I am not saying to dump acetone or motor oil in your reef tank. Or if you do, call me and let me know how that went. What I am saying is these are sources of organic carbon. After the BP oil spill, there were lots of happy heterotrophic bacteria in the Gulf. But not every source of organic carbon is obviously appropriate for a tank. Well, so just sort of summarize, how does it work? Well, the bacteria utilize these dissolved nutrients to live and grow. Once you address the carbon limitation, the bacteria can grow and build biofilms. And then the bacteria sequester the nutrients and build the biofilms to either be exported or subsequently mineralized into less problematic forms. And this occurs to a large extent in these biofilms. Biofilms grow everywhere in your tank. They grow on the insides of the glass, they grow on equipment, on corals, on rocks, on fish, on the substrate, in your filter, everywhere. And in these biofilms themselves, you're having a significant amount of nutrient processing. But one thing I want to sort of emphasize here is when we're talking about carbon dosing, everybody views it as an export methodology. I'm going to increase this biomass of bacteria The bacteria are going to fix or absorb or otherwise uptake these dissolved nutrients I want out of my system, and then the bacteria will get skimmed out or otherwise exported. Export's part of the picture, but I think even a more important part of the picture is that what's really occurring in these biofilms is mineralization of these nutrients. That the complete loop occurs from ammonia and ammonium from fish waste and food all the way through to nitrite, nitrate, and eventually to nitrogen gas. And the same with phosphate. So the net increase of bacteria in a balanced system also means you're going to have a net increase in the metabolic processing of these nutrients. So it's not just export we're worried about. Well, what happens to this? Once they absorb the carbon, what happens? The bacterial cells will catabolize or break down these organic carbon sources like ethanol and others into simpler molecules, and then they use these simpler molecules to build the structures they need to build: biofilms, DNA, cell membranes, and really cool stuff. Now let's talk about some of the commercial systems. Now we're going to get into the practical information. Typically, when you buy a commercial organic carbon system, it's going to have a bacterial source, an inoculant, plus some sort of organic carbon. The carbon sources differ from system to system, and some of the main commercial systems we'll talk about are Zeovit, which is probably the oldest widely available one. Prodibio, NeoZeo is Brightwell Aquatics' zeolite-based system, as is Ultralith, and then we're going to also talk about biopellets and solid polymers. Zeovit. Zeovit is a company in Germany started by a guy named Thomas Pohl, who probably had the first commercially available organic carbon system on the market. The core of any zeolite or zeovit or any similar system are these minerals, these rocks called zeolites. And it's not only just a zeolite, it's a specific kind of mineral called a clinoptilolite. The clinoptilolite is an aluminosilicate mineral, and you use them in a reactor, an upflow reactor. These zeolites are very, very porous, so they're a good substrate for bacterial growth. But there is and it's up to some debate, there's a chemical interaction that occurs between the biofilms that grow on these zeolites and the chemical structure of the zeolite themselves. One thing that Corral and Zoot, Thomas Pohl's company, says is that they claim that it absorbs ammonia and ammonium more readily than any other source and takes it out of the nitrogen loop, and therefore you got lower nutrients. I don't think that's accurate. I don't think clinoptilolites or certainly any related zeolite can absorb over a long period of time ammonia or ammonium in seawater, mainly because once the ammonium is absorbed into the zeolite, it's immediately dislodged by other ions, mainly potassium. But for whatever reason, whatever the mechanism is, clinoptilolites are an excellent bacterial growth medium. One thing to keep in mind is they will preferentially bind potassium over any other ion. Matter of fact, a recent study showed they will bind potassium and then sodium and then calcium and then magnesium in order of preference. We'll talk about potassium completion, and I'll tell you my sob story about that here in a minute. But just be aware that potassium is an important ion in any zeolite-based system. They're just an extremely effective media for bacterial growth. I've also heard it postulated that, it's hard to see this, but that perhaps some of these clinoptilolites have iron in them, or a significant part of iron, and there may be iron-reducing bacteria involved in this nitrogen cycle. I don't know. It's an effective media. Well, how do you use it? Well, you put it in one of these. This is a standard zeolite reactor, it's got an inner chamber in this outer chamber. So you can take that inner chamber out that's got perforated end caps. The water's pumped up through the inner chamber, and then once or twice a day, you grab this handle and you shake the inner chamber. What that does is it dislodges the biofilms that are growing on those zeolites for a couple of reasons. One, they're exported to the system and now become available bacterial plankton for corals that feed on bacterial plankton. And two, it causes a rapid additional growth of new biofilm on that substrate and an increase in the amount of nutrients taken out of the water column. So you've got a reactor filled with zeolites. You shake it twice daily to release this, they call it a mulm, back into the system. They recommend for the first few weeks that you cycle your reactor on and off for 3 hours. I'm not sure this is a valid recommendation anymore. I never do that when I'm setting up a zeolite or a zeovid system, but it's something to keep in mind. The bacterial product they sell is called Zeobac. The carbon source is called Zeostart 3. And then they also recommend that you add this stuff called ZeoFood, which is an additional carbon with an amino acid supplement. This is what this stuff looks like. It all comes in blue bottles. For guys that are really into zeolite, let me ask you this, and I always ask this before this presentation, and I neglected to do so. How many of you guys here use either vodka dosing, zeovit, or a similar organic carbon system? Okay, so some of you guys know what we're talking about here. The guys that are really heavy into zeovit, you can open up their cabinets and it's a sea of blue bottles. They make a wide range of supplements, some of which I like very much, others I don't care for. Regardless, there are special husbandry requirements. Let me disabuse you of this notion for anybody who's never used a zeolite-based system or zeovit. I think some people approach this as, well, this will make reefing easier. That I don't have to spend as much time working on my tanks. I won't have to do as many water changes. It requires an increased level of husbandry and attention. It's very effective at nutrient reduction. Any zeolite system is, especially zeovit. However, if you're not on top of it or don't have the time to test your water regularly and stay on top of your tank, this ain't the system for you. The abiotic parameters of your water, the non-biological parameters of your water are important. They suggest that you keep natural saltwater parameters throughout your system. Alkalinity and potassium are really, really important ions to watch. For some reason, well, let's just go through these. These are the general natural saltwater parameters. You're looking at, 410 to 420 really for calcium, magnesium around 1300. Alkalinity is critical. Be real careful getting above 7.5 DKH. Potassium around 400, and salinity 34 to 35 parts per thousand. Alkalinity stability, not only amount but stability is critical. You will see most zeovit tanks are heavily, we call them SPS, acropyrid-based tanks. But in many reports, and I've seen this, I've set up and used zeovit on over 6 different tanks over the years, and I've seen it in mine as well. If you get sustained alkalinity values over about 8 DKH, you'll start to see either bleaching or actual necrosis on the tips of acropyra. There's no cogent explanation I've ever heard as to why it happens, but it happens. So monitoring alkalinity is really critical. They discourage use of granular ferric oxide as a phosphate removal media. You're going to deplete nutrients really rapidly if you overdose zeovit or push zeovit too fast, especially when transitioning from a moderate nutrient to a low nutrient environment. you can lose corals really fast. So additional methodologies to reduce nutrients are just going to compound that problem. They seem to recommend shallow sand beds. There's been a lot of anecdotal reports of problems with people trying to run an existing deep sand bed with zeolite. I don't run deep sand beds anymore, and I've never run them with the zeovit system, but those reports are out there. They do want you to use carbon, granular activated carbon, but they suggest you use it passively. You're just going to use a little bit of it. And they just discourage the use of ozone and kalkwasser. Potassium can be rapidly depleted. As I showed you earlier, these tidalites preferentially absorb potassium. I had a situation, this was my, second or third zeovit tank, maybe 4 years ago. And I started noticing the crush, and it was full. It was about a 75-gallon tank, had a crop of colonies varying from softball to, a couple were volleyball size. A lot of them I'd grown from frags. You know how that goes. I started losing coral, started seeing necrosis. I couldn't figure out what was going on. I was testing like a madman. Every parameter I could think of, could not put my handle on. I keep on losing corals and keep on losing corals. Using a Coralline Zoot, a zeovit potassium test kit, because that was the only one at the time that was commercially available. Well, what it turns out is that test kit was faulty. The backup that I ordered from Coralline Zoot from another batch was faulty. And finally, when this was happening, another test kit came out, and I sent a sample off to a lab to get tested. And my potassium, instead of 390 to 400, was 170. And it was because I had a bad batch of salt water, but I didn't know it because I didn't have a good test kit. Now we're in a different situation. There's several test kits out there. Most of them are still real hard to read. The Salifert new one is a little better. But the best test for crashing potassium is red monoporic capricornus. If you can get if you're going to run a zeolite-based system, I strongly encourage you to put, even if you don't like the coral, stick it in a corner somewhere and grow a frag of red monicap, because that's one of your most reliable indicators for potassium depletion. The bad thing about potassium depletion, it's not like alkalinity or calcium or other ions where if you bring it back up gradually, you'll notice some improvements in your coral. Once you have a potassium crash, your corals probably aren't coming back. It's just too important of an ion. So be aware there's a potential for potassium issues. Also, I was running this, this sort of leads me into my recommendation that was zeovit. I really don't like zeovit on anything under a 100-gallon tank. And I've run it on smaller tanks. It's just too, the mineral imbalances can happen too quick to stay on top of. Salt mixes, it kind of goes all over the board. Coralline Zoot wants you to use theirs, the zeovit Reefer's Best, which is horribly expensive. The main thing is trying to find one that's got spot on natural saltwater parameters. A lot of guys, zeovit users, use Tropic Marin Pro Reef or the Deltec salt. ESV's got a good one. We'll get to water changes in a minute, but with the zeolite-based system, you're not going to be using a lot or doing a lot of major water changes, so it's not that big of a deal. Just stay on top of your parameters. You don't want to do a big water change with salt mix that's got a real high alkalinity, and now you got a high alkalinity problem. Overdose indicator, start 3 on the bacterial source. You'll start to get a brown bacterial film on the glass. That's a good indicator that you're dosing too much of the carbon. What are the benefits? This sounds like a nightmare scenario, so why would anybody want to do it? Well, it's really good. It's very effective. It does what it says it's going to do. It's also an effective feeding methodology. It's essentially a bacterioplankton generator. And for many species, that's an important feeding strategy. It's one of the most established commercial systems. There's really good support on zeovit.com, and it allows you to tweak. All the products are broken down into multiple units, so you can really tweak the individual components based on what you see and the reactions in your tank. What are the drawbacks? Well, it requires diligent attention. This is not a casual system. I don't think it can be very effective on smaller systems. I don't think, well, let me say this. I don't think it's as effective on a smaller system as it is on something above, say, about 100 gallons. And I think part of that is the available substrate just generally in the system for bacterial colonization. But also with some of the mineral imbalances that can occur, it's just really hard to stay on top of them with smaller volumes. It can rapidly deplete nutrients in established systems, with, especially if you've been running at a moderate or high level of nutrients for a long time and your corals have acclimated to that environment. You know, if you push zeolite, any zeolite system really hard, you can cause problems. Potassium depletion we've talked about. The conventional wisdom is it's expensive. I don't see it as that expensive because you're dosing such small amounts per unit of volume, but with a larger tank, it can get a little pricey. And I've got some issues with ZeoVit's quality control. I was tempted to ship Thomas Paul a box of dead acroporids for Christmas about 4 years ago. Didn't do it. But let's look at some eye candy. Why do we care? Well, because you can get a tank that looks like this. With sustained very low nutrients and a high bacterial population, we tend to see in some acroporids, depending on the genetic potential of the animal or the colony, very vibrant colors, some say even faded colors, but you tend to get really good colors because you're going to have a really low zooxanthellae density. This is Van Tilburg, Robert Van Tilburg. He's an old ZeoVit user, Dutch, has a really nice system. I love this guy, Juan Ferca, Spanish ZeoVit user. I just loved it because his Youngie or his acropora here grew so fast, when it hit the top of the water, it flattened out. Luc Loyen, a Belgian ZeoVit user. Again, incredibly vibrant colors. Frank Dorado, the Italian ZeoVit guy, has a beautiful tank. So we'll get to Prodibia. So that's ZeoVit. And there's 3 or 4 different manufacturers who use a zeolite-based system, but it's all basically the same. And all the husbandry issues I've identified are equally as applicable whether you're going to use Brightwell Aquatic ZeoVit or zeolite-based methodology or Fauna Marin's or anybody else's. Prodibio is a French company, and their system is very basic and it's very simple. It's a one inoculant biodigest and a carbon source in Bioptum. The cool thing about Prodibio is that it's dosed either once a week or every 2 weeks, both the biodigest and the Bioptum. It's a good solution for anyone who travels or just isn't quite ready to take the full step into an aggressive labile organic carbon dosing regimen. It's extremely mild, it's very safe. It's really hard, if not impossible, to completely overdose on this stuff. That being said, it's not as aggressive as zeolite or other carbon dosing systems. Use it only one or 2 weeks. It can be effective, it just takes longer. And you're not going to get necessarily the same nutrient reduction capability as you would in other systems, but it can be effective, it just takes longer. I like the biodigest as a general inoculant to use with DIY, carbon dosing, and other systems. Ching Chai, the Thai Acarist has been a Prodibio user for a long time. This is his old tank. I don't have shots of his new one. Here's a side view. Huge colonies. Neo Zeo is Brightwell's zeolite-based system. Just so that you know the breakdown on that, it's the same basic idea as Zeovit. It's zeolites in a reactor plus a carbon source. They're bacterial inoculants called Microbacter 7. Biofuels are carbon source. It's generally a little less expensive than Zeovit. Ultralith has one, or Fonamarin has one called Ultralith. Again, it's zeolites in a reactor plus a carbon source. Ultrabac is the bacteria. Ultrabio is the carbon source. As with most Fonamarin products, it's harder to find in the US and more expensive, but it has a wide range of adherents, especially in Europe. Polyp Lab, I'm actually using this system right now in one tank. It's a Canadian company. It's a 4-part system. Fuel is their carbon source. Genesis is their inoculant. Plus is like Coral Vitalizer. It's sort of a food analog, and then they do an amino acid product. I'm actually having pretty good luck with and results from using this system in connection with an algae scrubber. And I'll get to that algae scrubbers in a second. I think there's some synergies going on there. But I'm liking Polyp Lab, and I'm noticing really good reaction from my Acropora. Genesis, the bacteria fuels the carbon source. This is Greg Timms. He's a Montreal. He's been a long time Polyp Lab user. Beautiful tank. The present and the future, solid polymers. Anybody using biopellets? Okay. Of those who've used them, what's your experience? Like them, dislike them? Love them?
There's not much room for error.
Not much room for error?
Indifferent.
Indifferent. That's the kind of reactions I'm getting and the kind of experiences I've had.
Can I say something? With mine, I find it really, really easy. I mark my reactor. I keep my pellets at the same level. And I use one of those ones that has a little vortex going on. Because a lot of times I've gone through 2 or 3 reactors and they say it's only supposed to tumble or whatever. The one that I've got now that kind of swirls them in a vortex, I can't remember the name of it.
Yeah, it's J&S, isn't it?
Maybe, yeah. It works better than any other ones I've had.
Well,
I swear by it.
here's the deal the conclusions I'm drawing with solid polymers. First of all, let's talk about what they are. We're talking about biodegradable polymers. As of last count, I think there were 18 on the market. So everybody's coming out with a polymer. If they haven't
I've got
already.
one coming soon.
Yes. They're typically used in, you can use them in just like a regular filter box, but they're typically used in an upflow reactor for those who aren't aware of them. And they're a biodegradable polymer pellet. It was originally developed, these compounds were developed as a biodegradable packaging, plastic packaging material. The cool thing about them is they're actually synthesized by bacteria. And A. eutrophus is one of the main strains. And they grow this bacteria in a glucose substrate. And what they do is they've given them this bacteria a carbon source, but they deprive it of other nutrients. And as a starvation response mechanism, this bacteria actually generates PHB and PHBV, these polymers we put in our tanks. It's essentially bacteria food the bacteria is making because it's seeing starvation conditions. So it's like, uh-oh, I better make something to eat for later. So it's generated by bacteria. It's bacteria food made by bacteria. One kind of neat thing, at least conveniently, is it's not only a carbon source itself, it's also a physical substrate for development of biofilms in the bacteria. So it's effective depending on how it's manufactured. There's some bacterial plankton generation. It's not near as much, I don't think, as a zeolite reactor. Assuming a zeolite reactor produces any appreciable amount anyway, but you're getting into some bacterial generation. The carbon's limited to the reactor. This is a frequent manufacturer benefit that's claimed, is that, well, you're not dosing the whole tank, so you don't have to subject your other inhabitants to this carbon source. We're going to keep it in a reactor. Almost all of them, I mean, of the 18 I've looked at, 15 at least were polyhydroxyl butyrate, PHB. At least 2 of them are PHBV, which the EcoBac product, and ATB has a biopellet, which is the exact same thing, sourced from the same company. It's a PHB with a valerate ion attached to it. These compounds, PHB and PHBV, are similar to polycaprolactone chemically, which is the substance that's been in natural nitrate reducer and instant ocean product. It's been around for years. Oh, and Dr. Tim's is a PHA, which is slightly different than a PHB. That being said, we're not talking about a wide range of chemicals. It's not like one biopellet is significantly chemically different than another. From my understanding, I'm not a chemical engineer, but we're talking about the same classes of polymers. Now, is there really any difference? Well, I've noticed when I experimented with them that the PHBV, as in the Warner Marine EcoBac product, I got a little bit better phosphate reduction. But my general impression of these things, or experience with these things, is it's very system specific. You might install these polymers on your system and have great results. Balanced nitrate and phosphate reduction over time, stability in the system, coral's doing great. You might put it on your system and not have any results at all or very little. You might put it on your system and weird things may happen to your corals. I think the danger is very low. I'm not here saying that they're dangerous. It's just very system dependent. And one reason is it's a single source of organic carbon. And some of the other commercial systems and some of the DIY systems we're going to talk about, you're going to have multiple sources of organic carbon. And we're going to talk about why I think that's important. But essentially, when you have multiple sources of organic carbon, there's research that suggests that you're increasing the biodiversity of a biofilm, that you're increasing the amount in different types of strains in the biofilm, and that may result in a more robust nutrient reduction situation. But with the biodegradable polymer, you're limited to one polymer. They're hard to control. About the only thing you can control on these is the amount of the flow through the reactor. We're starting to see new reactors out that are changing the hydrodynamics of the water flow adjacent to the pellet, which has a direct impact on its effectiveness. But still, those are the only things you can really control: the amount of polymer in the media or in the reactor and the flow through the reactor. There's a lot of research out of wastewater treatment that show that the speed and the direction of the flow of the water next to the pellet, or next to the biofilm growing on the pellet, directly affects how thick that biofilm is going to be, how many different types of strains are in that biofilm, how effective and robust that biofilm is going to be. So until we can really figure out how we're going to control and optimize hydrodynamics, I think the technology is somewhat limited. This is an EcoBac. This is one of my old tanks. When EcoBac first came out, I sort of beta tested it for John Warner. I had good results on this tank. I tried it on other tanks and didn't have as stable of results. The other limiting issue with any solid polymer is with any source of organic carbon, whether it's vodka, whether it's polymer, whether it's a commercial product, there are certain species and strains of bacteria that are going to be more efficient at uptaking, catabolizing, breaking down that source of carbon than other strains. In other words, all carbons aren't equal to all heterotrophic bacteria. So there's probably a limited range of bacterias that are efficient at breaking down the polymers in the solid polymer stuff. If you've got it in your tank, great. You're probably going to have great results with biopellets. If you're not, I don't know nobody's really identified which specific strains are very efficient thermodynamically at breaking this stuff down. There's some manufacturers who claim they have, but they won't send me the research, so I don't know. Long story short, try it. It may work great on your system, but it may not. It's real hit or miss. This is another tank. It's a bad picture, but I set up and I was running NPX bioplastics on this and had pretty good results for about 8 months, and then they just didn't work very well anymore. This new product, John Warner at Warner Marine's coming out with a non-woven fiber, basically a cloth made out of PHBV that seems to have some interesting properties in terms of being more effective at reducing phosphates. Any of this stuff is probably going to get your nitrates down. Nitrates are a fairly easy nutrient in my experience to address, but this is just a cloth that's good that you can put in box filters and other types of applications that should be on the market in the next 6 months. I've been experimenting with this stuff. It's a long chain polymer from Tropic Marine called Reef Active. It's the same stuff they put in their bioactive salt, sea salt. I'm having really good results using this carbon source in connection with an algae scrubber. And there's some sort of synergy I'm seeing there between that carbon source and the way the algae scrubber is functioning. But this stuff was developed, and here's what the manufacturer says, that it binds with nutrients to make them more available to certain strains of bacteria. But after talking with the guy that developed this, I think what he's really getting at is his research shows that this particular long chain polymer is more analogous to the types of organic polymers or carbons that are available on a reef, that are available to the coral holobiont, the whole coral on reefs. And so it's more of an analog to coral mucus. I'm having pretty good luck with the stuff. I've just started it over the last 6 months, so jury's still out, but I'm liking what I'm seeing. It was developed by Hans Werner Balling. You might be familiar with the Balling system or heard of the Balling system. He's a marine scientist in Germany. Pretty smart guy.
So have you not tried this without the algae scrubber then?
I have not.
Is it a biopellet or what?
It's powder. You just mix a little bit in a beaker and pour it in 3 times a week. I'm real anxious, That's all I know about it, man. DIY methodologies. When we're talking about DIY, we're talking about stuff that you can pull off the shelf. Vodka, vinegar, the sugars, vitamin C, and then we're talking about mixing some or all of these ingredients together. Yes, sir?
Got a question for you. I ran the vodka with the microvac 7 for a little over a year. I had good success with it, and I guess from my laziness, I gave it up. Started a new system. Lately, I've been reading up just to see about different ways to go besides vodka. I found a little bit on honey. And I was curious what you thought about that. Apparently, it's got the amino acids plus your carbon salts with the sugar. I couldn't find a lot about it, so I was just curious if you have any experience with that. Or
I have not dosed honey in my reef tank.
somebody had it, they were cut it very big. It was a very
Well, here's the problem is, every honey's different. It's based on location. So there's not, and the flour's available, and so how can you know from bottle to bottle you're getting any consistency?
Right, because that's what the people put, is that they were getting it from a bee farm, and they said they didn't recommend using any kind of off-the-shelf products because you don't know what's in there. I was just curious if you heard anything about it, if you heard anybody tried it, or any
Man,
success.
I've heard of people using rice husks as a DIY polymer. I've heard of honey, but
No, nothing good. So I just-
try it, let me know. I'm all for experimentation, man, especially when it's your time.
You do something about it, watch it.
Oh, yeah, let's see how you are. Okay, vodka. Vodka is generally, we're talking about ethanol, and we could be talking about other sources of ethanol, but, vodka is a fairly effective carbon source that appears to be readily utilized by a wide range of heterotrophic bacteria. It's cheap, as long as you don't drink it. Don't use flavored vodka, because I don't know what it's in it, or again, if you do use it, let me know.
Use honey flavored.
Yeah, use honey flavor, there you go. I'm gonna give you some rough dosing guidelines that I've used over the years that seem to work for me. And when I do, I'm talking about 80 proof, which is 40% alcohol.
Talk about.
There's other sources of ethanol, gin, shine. What's grain alcohol called?
White lightning.
Moonshine.
Well, that's the other.
Everclear.
Everclear, I can't imagine scientifically there's much difference between using 80 proof of one versus 80 proof of another, given similar lack of any sort of contaminants. I just know, generally from experience, vodka is a pretty clean source of ethanol. One thing you may see with vodka dosing is an increase in cyanobacteria. In those instances, my recommendation is to reduce dosages to about half and pursue conventional cyanobacteria remediation strategies, increase flow, siphon it out, reduce photo period. Vinegar is another available and perfectly appropriate source of organic carbon. We're using the acetic acid in the vinegar. It's not as potent. Generally, a good rule of thumb is vinegars maybe about a sixth as potent as vodka, although that's just a broad and sweeping generalization. With overdose of vinegar, sometimes you'll see bacterial mats, sort of a white slime bacterial mats that reduced dosages seems to alleviate.
I've actually had on my glass.
Yeah,
When you overdose, I dose vinegar, and I've had really good success, especially with Zoas, believe it or not.
really?
Zoas really like just mat the rocks
Yep.
with vinegar.
Yeah, so you got the white slime?
I've got the white slime on my glass that I reduced.
Do you reduce it and it clears up?
Yeah, I used 3/4 a cup to 12 gallons, and I went to half a cup, and it went down. So
Okay. Well, cool. So I'm on track. Sugar has also been used. There's some dangers associated with sugar. It's a very effective bacterial food. There's no question about it. But there's some dangers involved. When we're talking about sucrose, table sugar, it's a disaccharide, essentially a glucose and a fructose molecule that are chemically joined. And it can be effective. I think glucose, back when I was experimenting with this stuff, I found to be a little bit safer. The problem with any sugars, and almost any sugar is going to be processed fairly quickly back into glucose. Glucose is directly absorbed by a wide range of animals, including corals. There's a lot of studies that seem to indicate that the increase of glucose levels on coral epidermis may be somehow associated with bleaching events or other problems. And I've seen this both in my tanks and others with a heavy sugar component. Occasionally you'll start to see darkening or even loss of scalemia, trachyphilia, and some of the related single polyp corals. So, sugar is effective. If you're going to use it in very, very small amounts. Vitamin C, was started by xanthan palithoa keepers, enthusiasts, been using it for years. And it seems to have a positive effect, especially initially for me. It may be an effective carbon source. One thing that keep in mind is, in alkaline conditions like seawater, it'll eventually metabolize into hydrogen peroxide. Now that's probably immediately metabolized into something else and may not be dangerous in on itself, or it may be, but it's just something to keep in mind. Nevertheless, if you're going to use one of these DIYs, I would strongly consider using it as a mixed solution more than one. And why? It's been pretty well documented in scientific literature that multiple carbon sources will promote bacterial strain diversity in a biofilm. Now, it is not true that if you just use one carbon source, you'll develop a monoculture. You might develop a dominant strain, but you're not going to develop one strain that'll exclude all other bacterial issues. So that's not a real concern. But I've just noticed in my systems using various mixtures